Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Continuous random variables. But for the mid-semester exam, they'll be covered on the final exam. Having said that, I can't really give a week cut-off because I did say some things about the Poisson earlier this week and so on. So it's more the content covered in, so it's not like nothing this week is covered, because at least what I said about discrete variables on Monday is covered, but nothing about continuous random variables or densities for the mid-semester exam. And that is on Tuesday, as a reminder. And your assignment's also due on Tuesday. I'll have my normal office hours after this lecture if anyone wants to come to my office, or you can try and catch me as I leave as well. Now, let's continue with, I do want to get we've done a lot of the generalities of continuous random variables, so let's review those. Continuous random variables have, so let's say it's a random variable x, and have a very important piece of data that comes with it, called the density function, someone said, yep, PDF, which is also called probability density function. I generally use f subscript x of x. Constraints on that's greater than or equal to 0 everywhere, and also that the integral over all possible values. Now, I write minus infinity to infinity. If it's a restricted range, then you just imagine it being 0 off that range. F dx equals 1, because that is, of course, the probability of lying anywhere on the real line. And then if I want the expected value, what do I integrate? Someone? Yeah, x times density. And remember, I like you to think of this as this is the probability that, I mean, I put in inverted commas because we don't actually believe in infinitesimals, but this is that x lies in a very short range of width dx. So where kind of dx is an infinitesimal. That's what you think about it. So the density, the density is just a number. The density times the length is the probability of being in a short interval. It's worth noting that the probability that x is between, I'll just say a and a plus t. Often I write a to b. That is, of course, by definition, and whether I include equals or not doesn't make any difference, a to a plus t, f x of x dx. And that is equal to, now I'll just say there's a little assumption for here, but I'll say that this is approximately equal to, I'll even say, now, I'll say it in a slightly more advanced mathematical way, but you don't need to know exactly what this means. I'll say that this probability, if t is small, we can approximate this. This is the density at one point on the interval, let's say a, times, and then we're imagining t shrinking and shrinking to 0, times the length of the interval, which is t, and then that is what it is, but it's not exactly that, because that would only be true if t was sort of infinitely small. So I can say that there's 1 plus little o of 1. Now, little o is probably as t goes down to 0. Another way to say that, probably a nicer way to say that is just that probability that a less than or equal to x. You see, I want to say something slightly more precise than just approximately, because approximately is not a really precise word. F of x a times t as t tends to 0. Now, unfortunately, what I've told you here is not always true. It is not always true. It's most of the time true. And I just want to put in the proviso that make sure that this will be always true. By the way, if anyone hasn't seen this symbol, it's a totally different symbol from when we're saying it has a distribution. This means asymptotic to. Okay. F is asymptotic to g if the ratio tends to 1. So it's about a limit. Okay. And the asymptotic 2 happens for t very small. It doesn't say anything for t large. Okay. Now, I'll just have to put in this proviso so I'm not saying false things on your slides. So long as... The key thing is that the density should be a good approximation for the probability, not just at that point, but around that point. For that to be the case, we're putting a little bit of a proviso on the density function. And I'll even remind you of a popular density function that we talked about a lot before. We'll do the more general one, from A to B. Right, this is a uniform on the interval A to B. This is the example that I missed. Now, if I do this, then there's actually an arbitrariness about how we define the density function. I think I defined it including the top points before, but because it's a jump, it's kind of arbitrary. I could have defined it using the bottom points. So if I had defined my density function, you see, that's an unfortunate reality about density functions. When there are jumps, there's not a unique way to choose it. It's actually totally arbitrary whether you put the jump continuous on the left or continuous on the right or continuous, on neither side with some totally unrelated value. The reason is when you integrate, the value at a single point of jump makes no difference, whether it's on the left or the right. So unlike the PMF, the PDF is actually not technically unique. It's unique up to changes on a finite set of values, or even if you want to do measure theory, it's unique up to changes on a set of measure 0, which is a whole another kettle of fish. So we won't worry about that. But the reality is, when you have a point that it's not continuous at, it's kind of, I could have defined the density at A to be 0. And then the probability of being between A and A plus T, you would only get the right value if the density was here rather than there. So for this to be true, that would be so long as f subscript x is continuous at x. And you might say, why does it have to be continuous? It could just be right continuous for this example. Yeah, and so that's correct. Because this interval lies to the right of A, it would have to be right continuous. And similarly, but it's easier just to remember continuous because what this is claiming is the probability of being between A and A plus T is like the density times T. Well, that would actually only be true if the density took the value here. If you ask the question, why can't we just define it up here, there's nothing special about intervals on the right. We might want to talk about intervals on the left. Probability that A minus T is less than or equal to X, less than or equal to A. Same question is going to be asymptotic. So don't worry about little o notation if you don't like. If you haven't seen that, that means something. It actually means nothing other than something that tends to 0. Okay, so that's kind of a complicated way to say it. So maybe this asymptotic is a better thing. Probability A minus T less than or equal to X less than or equal to A. That's asymptotic once again to fx of A times T. Why T? Because T is the length of the interval. But so long as, fx is left continuous at A. And of course, if you want an interval that spans T on both sides, you would have to have both left and right continuous, in other words, continuous at A. Okay, so that's, I like to say this because some people think integrals are the only things you can do with densities. Even if you can't integrate, you can still say something, and that's, it does follow from abstract theory of integration, because for a continuous function, the integral is close to the value times the length of the interval. So that's the reason for that. That's all I'm going to say about the generalities for now. Let's get on to some famous continuous random variables. But before I want to do, so the uniform is kind of already one famous one. It has the property that the chance of being in any fixed length interval within the range has the same probability. Now, no other continuous random variable has that property that that you have a range and every equal length interval has the same probability. So that's why it's called uniform. That should be kind of easy to see, but I'm not going to go into more detail about that. But let's talk about other classifying properties. And one of them is the loss of memory property. And before we do that in the continuum, I actually want to say that we've already done this in the discrete, but we probably didn't talk about it. So And the loss of memory property in words, roughly, is, okay, if it's about a waiting time. If you've waited time t and not arrived yet, okay, so there's something that you're expecting to arrive, the remaining time, so there's the remaining waiting time, you're waiting for a certain event to happen, has the same distribution. You had an original waiting time distribution, you wait a certain time, conditional, so when you say if, that means a conditional probability, the remaining time has the same distribution. Okay, so that's in words what it means. But now we're going to try and figure that out. Just in terms of discrete, let's say we're just saying things that arrive at integer times, no fractional times. Do we already know a variable that has this property? You wait for a certain thing to happen, and then if it hasn't happened, it's just as if you were starting again from the beginning. Geometric, exactly right. You might think that this generalizes to all negative binomial or something like that. It doesn't generalize to negative binomial because, say, negative binomial 2p means I'm waiting for the second heads to be flipped. And if I've seen the first, I'm waiting for the second heads hasn't come yet. Well, I'm in a materially different position depending on whether I've seen the first heads or not. So you can't tell just based on the fact that I've waited 10 turns, because 10 turns might have included the first heads or it might not, and they wouldn't have the same distribution. So negative binomial does not have the loss of memory property unless it's k equals 1, which is geometric. So I'll just verify this for you. Let n be geometric p. Okay, so this is the loss of memory property in the continuum. We know the chance that n is greater than little n. It's actually, you may or may not have calculated the CDF of this. In case, well, it doesn't really matter. You can do it just by summing up the PDF. N equals 1 to infinity of, remember it's 1 minus p to the k minus 1 times p. Now that is the initial yeah, sorry about that. Okay, if I'm to do this sum, then I have to do p 1 minus p to the n, and then I have to do 1 minus 1 over 1 minus the common factor. So that of course cancels out the p. So the probability of n being greater than n is 1 minus p to the n. And by the way, I don't know whether I really need to do this calculation, because you can sort of see from the description in terms of waiting for the first independent, first of the independent trials that is a success. You can see that if the first n are the failures, then the remaining ones are just independent trials once again. So the remaining time is still a geometric. You can see it kind of from that description. But nevertheless, let's verify it by a conditional probability calculation, which is the additional waiting time. Remember that this is additional waiting time. Okay? So the probability that the additional waiting time is k, but I have to condition that I have already waited a certain number of times without success. So to say that capital N is greater than little n is to say that I have already waited n turns without success, because capital N is the first success. So if I've waited n turns without success, I know that it's strictly greater than little n. That's equal to, well, I can just write it, 1 minus p to the power. Now it has to be n equals little n plus k, so n plus k minus 1 p divided by 1 minus p to the power n, which is, of course, 1 minus p to the power k minus 1 p. Therefore, we'll say it as this way. The conditional distribution, which means exactly what you think about, the probability is conditional on a certain event. It's conditional distribution of the additional time, waiting time, additional waiting time n minus n, given the event, of course, that n is greater than n, has the distribution. This is a conditional distribution. We just have to recognize that, which is geometric p. So sometimes people might say, if you try to do this in notation, that's probably not a totally standard notation, n minus n conditional on n greater than n as the distribution. So that's sort of, sometimes people say this when we're talking about the conditional distribution. Geometric P, which another way to say that is it has the same distribution as n itself. So there's the distribution of the waiting time, and there's the distribution of the additional waiting time given that n is, you know. So this is a funny notation for the conditional distribution. And once again, equals with a d sign above it means that they're not the same random variable, of course, but they have the same distribution. Okay, so let's do this in the continuum now. The key fact about that, okay, so if you're thinking about what exactly this means, this is true for any natural number. You know? This statement is true if you've waited 10 turns. It's not true if I've waited 10 and a half turns, because the extra times after 10 and a half is, you know, it'll be a fraction, it won't be geometric. So that loss of memory property is true only for integer waiting times. We want to try one that'll be true for any number of, any waiting time at all that you like. So suppose, and so the waiting time should then be any positive real number. If you think about why it has to start at 0, it has to start at 0 because conditional that I've waited any real amount of time, it could happen just a millisecond after that. So there's no way to, if something has a real time loss of memory property, there is no way that you're not going to get waiting times very near 0, because you could have waited just before it happened, and then once again it'll happen just near 0. So it has to be a density, and clearly we don't want any negative waiting times. So suppose x has a continuous distribution. Now I'm actually going to put continuous in brackets because we won't need that to make the derivation, but it's, you know, we could assume it has an arbitrary distribution. Just the real number time loss of memory property will make our important difference, such that, once again, the probability of the conditional, I'll just write it in words, distribution of x minus a certain waiting time, given that we had to wait that long in the first place, is the same as the unconditional. Now, you don't have to say the word unconditional, but I'm just putting it in to be unambiguous. The unconditional distribution of x. It has to be the same as the variable you started with. That's the loss of memory. It looks the same if you've waited a bit. Okay. Then, now you could do this in terms of CDFs, but CDFs are they're just a convention and they go to the left. So I don't want to go to the left, I want to go to the right. So I won't even write down CDF, but this is, of course, if you want the right tail, you do 1 minus the CDF. So the probability that x is greater than y, given that x is greater than x, has to be the same as, let's do it this way. If x and y are positive numbers, then the chance of going y additional time past the waiting time x, given that you're bigger than x, has to be equal to the probability that x is greater than y to begin with. You see, because this is the conditional distribution of, you know, capital X minus little x being bigger than y, and this is the unconditional distribution of x being greater than y. So the loss of memory property says that, i.e. probability that, now let's just expand all this out. This is, of course, a ratio. First thing, you'll have to think of, you know, probability x is greater than y plus x. Intersect x bigger than x. But of course, these are both waiting times. So this event is a sub-event of that event. So I don't need to intersect. Divided by probability x greater than x equals probability x greater than y. So I'm now going to cross-multiply and put that on the right-hand side. X greater than x times probability that x is greater than y. So this is an interesting function. The function of being, sometimes it's called the survival function. If you, this is not super, well, some people use it. The survival function is 1 minus the CDF, right? It's the chance of surviving that long if it's a waiting time. So that's sometimes a word that's used. So the survival function has a multiplicative property. Okay? Now these are probabilities. Once again, let's just do a little. It would be nicer if I had everything additive rather than multiplicative. Let's just do it log p. And because probabilities are less than 1, let's talk about minus log of p x greater than y plus x. Taking minus log means that the product becomes a sum, so minus log probability x greater than x minus log probability x greater than y. So if let's give this function a name. I'm not going to use f because that's often the density function, but if g of x is minus log probability of x greater than x, then this function g is an additive function. Okay, if that may not be a standard word, so I'll say what it means. G of x plus y, right, that's what we had on the left-hand side, equals g of x plus g of y for all. Now, it's true that we only did this for x and y greater than 0. Of course, g is only defined really for, well, if I were to put in negative numbers into either side of that, I would get silly answers because the probability of being greater than -1 is just 1. So the formulas are not going to be true for negative x and y. I'll restrict to positive x and y. Fact, now this, by the way, can anyone think of any additive functions on the real? Okay. So g has to be a function defined on all positive real numbers, and it has to be additive. Can anyone think of any such function? Like just a function that has this star relation. There's a pretty easy one. Does g of x equals x plus 1 work? It's a trick question. You can't add 1 because then you'd get a plus 2 on the right and a plus 1 on the left. So you can't add a constant. So g of x equals x plus 1 does not work. But what's a function that does work? Linear functions that go through the origin. That's right. Yeah. Well, by the proper definition of linear functions do have to go through the origin. So yes, linear functions work. Now, there's a sad fact that if we're talking about all real numbers, that's kind of a very large space. And if you don't put one extra condition, people can come up with silly examples of things that are not linear functions that are additive. And they really are silly because they're not continuous. They dance around like anything. So they're not kind of real interesting things. So we need one more condition. The only... but luckily, and sometimes you talk about continuity, but as I said, CDFs are not necessarily continuous, so we don't want to impose continuity. But something that's almost as good as continuity or better, and is easier in this case, is monotonicity. Monotonic means either strictly increasing or strictly decreasing. So you'll note that as x increases, the probability of x being, capital X being greater than little x, decreases. Chance of being, greater than 10 is less than chance of being greater than 5. So that's monotonic. Now, I've taken minus log, so that's the opposite direction. So since that one was decreasing, this must be an increasing, okay, additive function. Or at least non-decreasing, but I'll even say that, non-decreasing. It turns out that it will be increasing. It is a non-decreasing additive function. The only non-decreasing additive functions are the ones that you mentioned. Okay. By the way, how would you do this? You'd start with g of 1, that's just some value, c, or you'd call it lambda. G of x equals lambda x for any lambda. Now, I guess I said non-decreasing rather than increasing. So lambda could be equal to 0. Then it's just g of x equals 0 all the time. Now, let's not go into the proof fully, but this can be done relatively easily. Of course, you would let lambda be g of 1. Addition, get a g of n equals lambda n for n. Right? And then addition in a different way. So if you add lots of g of 1 over n, you add lots of g of 1 over n's and you get g of 1, which is lambda. So g of 1 over n equals lambda over n, because whatever g of 1 over n has to be something that you add at n times and you get g of 1, which is lambda. So, add again, if you add all those things, g of, I'll just say m over n is equal to lambda m over n. So we're fine for positive rationals. And then monotonicity, which is a fancy word for increasing or decreasing. Monotonicity says that g of r equals lambda r for all real r. Okay. So the monotonicity is what goes from rationals to reals. Otherwise, you could theoretically have different values and different cosets of rationals, which is silly. Okay. So anyway, fact is done. So conclusion, there exists a lambda such that the probability that x is greater than, and by the way, lambda should be, let's say, greater than or equal to 0. X greater than little x is equal to e to the minus, because I took minus log, e to the minus lambda x. Okay? And that means probability that, so this is for all x greater than 0. Probability that x is less than or equal to x equals 1 minus e to the minus lambda x. Now, I'll just say, you might be wondering whether, just because you've done a derivation, it might not actually give you a valid distribution, but of course this one does. You have to check, and what would, by the way, what would the CDF be for all x less than or equal to 0? What's the value of, what's the chance of being less than or equal to 0? Like, this is a waiting time, right? So I've concluded that the chance of being over here, if that's x, then this area is e to the minus lambda x. It is a waiting time. It should always be positive. So the probability of being less than or equal to 0 is 0. Yeah, so that was one of those things that I said kind of went without saying, but I'm just, I didn't really have to say that. But so this is a CDF. It's easy to check that it is. It goes to 0 on the left, goes to 1 on the right. So there's no other problem. The PDF, so whenever the CDF has a continuous derivative, then that is the PDF. So is little f x of x is d by dx of the CDF, 1 minus e to the minus lambda x, of course for x positive, which is equal to lambda e to the lambda x minus lambda x, positive. X is called a, naturally enough, exponential lambda. Random variable. So this exponential lambda random variable has a more powerful waiting time relation than the geometric one. It's valid for all positive waiting times, not just integer positive waiting times. Okay, so that is exponential lambda. Now that we've got it and we've got a PDF, we might as well do our exercises and actually calculate. Well, let's just do the mean. It should be easy enough. So I'm going to integrate x e to the minus lambda x dx. Now, someone tell me what, sorry. The density is lambda e to the minus x, so I have to put lambda e to the minus x times the value. And someone tell me my limits of integration. Yep, those are the possible values. Now, this is arguably integration by parts, if you want to do this. So for those of you who don't like integration by parts, you would probably prefer to do an MGF, which is, for the MGF, instead of x, you put e to the lambda x, or e to the tx, your expected value of e to the tx. So because Okay. For those of you who don't remember, expected e to the tx, which is, of course, the moment generating function evaluated at t, that can be done in the same way, 0 to infinity lambda. In fact, maybe to avoid the... It just shows you that sometimes the simple moments are not necessarily any easier. E to the tx is the minus lambda x dx. Now this is going to be a lot easier because you just have t minus lambda as a coefficient of x. So that's lambda e to the t minus lambda x divided by t minus lambda. And then I have to evaluate that from 0 to infinity. So the MGF is actually a lot easier than doing the integration by parts. I would get lambda e to t minus lambda x, t minus lambda. I would get, well, I think it's just lambda over lambda minus t, isn't it? Okay, so a very, very simple MGF. So I'll let you then differentiate that yourself, but pretty clearly the expected value of x is not actually lambda, it's 1 over lambda. Okay, so if I differentiated that, I'd get lambda over lambda minus t squared, substitute in t equals 0. I would get 1 over lambda. And I guess I better give you the variance as well. So, okay, maybe I won't actually write out the calculation. Remember, I differentiated once, I got lambda over lambda minus t squared. There's no minus sign because the minus from the differentiation cancels with the minus from the minus t. Okay, so the variance you'll get 2 lambda divided by lambda minus t cubed. Ex squared, you'd get 2 lambda over lambda minus t cubed. When t is 0, that's 2 divided by lambda squared. Okay? So ex squared equals 2 divided by lambda squared. So that means variance of x. How do I put these together to get the variance? I always take the second moment minus the square of the first moment, right? That's the calculation point. So 2 over lambda squared minus 1 over lambda squared. Okay, so variance is 1 over lambda squared. So the interestingly, this shouldn't be surprising because you should think of the exponential as kind of a continuous time version of the geometric. The geometric, of course, had mean 1 over p, variance 1 minus p over p squared. But the 1 minus p, if you think of a very small p, is pretty much the same as 1. So the mean and the standard deviation of this are pretty much the same, which is very different from the Poisson, if you're thinking back to Poisson. The Poisson has a mean of lambda and variance the same, so the standard deviation is sort of the square root of the mean. So if the Poisson is away from 0, then it tends to there's very unlikely to be near 0. That's totally different from exponential. As you can see from, it's just, this is the shape of an exponential. We now know that y equals lambda e to the minus lambda x. It's the shape of an exponential. So no matter what lambda is, you've got a decent chance of being near the origin. That never goes away. Poisson, by contrast, ends up making a bell curve shape away from the origin. So I know Poisson is discrete. We can do a continuous version of that a bit later. Okay, so that's all I'm planning to say about loss of memory for now. And by the way, let's just talk about it's worth mentioning, since I've done this mx of t, this calculation is technically not true for all t. For this calculation, I need a constraint on t. Because you can easily plug in the formula and get it, but this will only converge to a finite integral if the infinity component of this tends to 0. Now what is when you let t tend to infinity, when you let x tend to infinity here, you want this to be near 0. So what's the condition? It has to be e to something very negative rather than e to something very positive, doesn't it? Because, you know, if you had... By the way, there's all sorts of problems here. You'd also get a negative denominator if you had t greater than lambda. Okay, the denominator's already negative, but you're subtracting one from the other. Anyway, the main problem is that you have blow-up. If t is greater than lambda, then it's e to a very large positive, so that's not going to give you any convergent integral. The moment-generating function requires a convergent integral. That's absolutely required. So t less than lambda. So if you think back to when we talked about moment-generating functions, luckily lambda is positive. So this function, this variable still has a, it has an exponential moment. That just means it's defined around 0. But it's not quite as good as some, like the normal, which we'll get to, or the binomial or any others that have, or the Poisson, which have infinitely many moments. They, this just has, which have, infinite radius of convergence for the MGF. Okay, so that's exponential. Now, I want to get on to the normal, but are there any questions about loss of memory or exponential before I do that? No. Okay, so to do the normal, I could just write down a formula, and then we would have some trouble checking that it integrated to 1. So you probably all know the formula anyway. So I'm trying to do something a bit more interesting and also show you where this comes from. So let's talk about binomial. Let's let k be binomial 2n, 1/2. Now it's possible to do this for actually any binomial, but I'm going to make the simplest possible choice because by having an even number, I know exactly where the centre is. It's n. That's the expectation. And I'm also I know that the variance is 2n times 1/4, so variance is n over 2. We're going to be able to get some pretty precise description of this. And once again, we even did some testing of this in R, and you can do more if you like. It does look a lot like that once you have n large. This is also nice and symmetrical between n and 1 minus n. So now so that means it'll be good enough just to only do one side of this. So I'm going to get something even more precise than what the central limit theorem says. You will have heard of the central limit theorem from your first calculus course, which says that whenever you're adding up a large number of independent random variables, so long as they all have a variance, then the distribution tends to a normal. So we're going to, for this specific case, not for every case, we're going to get something more specific. Not just that the distribution tends to a normal, but even that the PMF, appropriately scaled, converges to what will turn out to be the normal PDF. So let's prove that. And K, okay, is, just a reminder, we will need this, is equal to 2n choose K, 1/2 to the... So the 1/2 makes things easier also because of this cancellation, half to the K, 1/2 to the power n minus K. So that's equals 1 over 2 to the power, 2n of course. 1 over 2 to the power 2n choose K. So I'm just going to let t be K minus n. That's just a bit nicer because that will be centred around 0. Okay. So the probability that capital T is equal to little t is equal to 1 over 2 to the power 2n. 2n choose, so I have to get k, which is of course n plus t. That might not look like an improvement, but it is. So we're going to actually do the asymptotics of this as n tends to infinity, and we're going to have to figure out what the appropriate range of t's is. As you see from experiment pretty quickly, if t if t remains a certain percentage of the total, if t is like 75% of the total, you'll notice that this is just vanishingly small. And if t is like, any fixed proportion, it'll be vanishingly small. What you actually need is t to get closer and closer to the middle as n gets larger. And you probably also know that the correct scaling is the square root. But all of that will come out in the wash when we do the calculation. So first of all, to do this, I just want us to remember that we can do it this way. By the way, whether I did n plus t or n minus t, that would be the same. 2 to the power 2n, because of the symmetry, n minus t. Okay. So now, I want to actually write that out with variables. So this will be a factor that has the next thing that I'm going to do is that I'm not actually going to write this out in full detail. In fact, I'm going to compare how does it compare to 2n choose n. That's going to be our reference because that's the t equals 0 case. That's going to be the center of our distribution. That is, k equals n, which is the same as t equals 0. That's where this center is. We're going to do the asymptotics of what this actual probability of being t is. And let's put in, how do I fix it? Well, that has n, this thing has n factors on the top and n factors on the bottom. I actually want, arguably if I do it this way, I want n extra factors on the top and n extra factors on the bottom. So the extra factors on the top are going to be n minus 1, n minus 2, n minus t plus 1. Because remember, you always have to have the same number of factors on the top as the bottom when you're doing this binomial coefficient. And on the bottom, I have the extra factors are going to be n plus t minus 1, all the way down to n. I'm actually going to do that in the other order, so in increasing order. N times n plus 1, n plus 2, and I got it wrong here. Instead of n minus t plus 1, I want a total of t factors, so that's actually n minus t factors. Okay, so this is n plus t. Okay, something's... Sorry about that. Okay. I was correct first time, so what I need, okay, let's get the factors correct. n minus t plus 1. Okay, so that n is cancelling an n that was on the denominator due to that. You can double check that that's right. But that is the formula for when you expand out the binomial coefficient. And the reason I'm just leaving this one sitting here is because that is constant. Okay, that one's not going to change with t. So let us. So that is 1 over 2 to the power 2n choose n. That's our constant part. And now I'm going to do exponential of something. If you've never seen someone write exp before, that's a cheap thing because sometimes exp of u is equal to e to the u. Sometimes you don't want to put everything in an exponent, so it's the exponential function. That's all that it means. So exp of, I'm going to sum up all these logs. Sum I equals 1 to t minus 1 log of I'll write it the same way first and then I'll change it. Log of n minus I. So that's what we have on the numerator. On the denominator we have log of n plus I. So I'm matching the n minus 1 and the n plus 1 together, the n minus 2 and the n plus 2. And then on the denominator there's also one extra term, the n plus t, which does not occur on the numerator. So then I have to subtract log n plus t. Okay? And also there's a log n on the numerator. So that's clearing that all out. Now it turns out all these n's are getting in the way here because I don't like to. I'm actually going to want to expand out what the log is because all of these. I'm imagining something that is centered around k equals n, it's the deviation from n, the i's will be very small compared to n. And that means the expansion of log would be best if it was around 1 rather than around n. And to do that, I'm going to replace, probably it would have been better to do it on the previous line. Whenever I have n, I'm just going to divide top and bottom by n. There's n, so if I divide, effectively what I've done is in the expression, divide top and bottom by n to the power t. That's really what I've done when I go to the next line. So it'll be a bit more convenient to write 1 over 2 to the power 2n. 2n choose n, exponential of... so all these n's become 1, and all the i's become I over n. So sum I equals 1 to t minus 1 of log of 1 minus I over n minus log of 1 plus I over n. Okay? And then that's the sum, but there's this last term, log n minus t. Well, log n cancels with log of n plus t. So what I'm left over is log of 1 plus t over n. Okay. Now let's expand those out using the Taylor series for log. If you don't remember that, all you need to know is that log of 1 minus x is equal to minus x squared, minus x squared over 2 plus lower order terms. Okay. So order of x cubed. If we plug that in, we get same thing out the front, 1 over 2 to the power 2n, 2n choose n, exponential of sum I equals 1 to t minus 1. So now here's the thing. That's the great cancellation that happens. I'm going to get a minus I over n, but I'm also going to get a plus I over n. So the minus x terms will cancel. The minus x squared terms over 2 will not cancel. So minus I over n squared divided by 2. Here, x is equal to I over n in that expansion. Minus I over n squared over 2. That's what I'm summing. And then also, so plus order of, how many terms did I add? T, because I is less than t. So if you don't understand the big O notation, just that's just a way of keeping track of the errors. So the error is no more than t times an x cubed term, which is t squared over 2. T times t over n squared. Okay. And then, but I have to add in this last term, minus log of 1 plus t over n, that is equal to t over n plus, of course, t squared over 2n squared, plus, and then the same error term. Okay, so now I have to simplify all this. It's 1 over 2 to the power 2n, 2n choose n. Now, the great thing here that's happening is that I've got exp of 1 over n squared. Sum I equals 1 to t minus 1 of I squared. There's actually an expression for that. T minus 1 2t minus 1 divided by 3. That's just a formula for summing up the squares of the first t minus 1 integers, and then I have to divide that by 2, so it becomes divided by 6. And then minus, once again, t over n plus t squared over 2n squared plus lower order terms. Okay, so at this point I've run out of time to finish the expansion, but let's even say that Stirling's formula, the last thing that we need to verify there is Stirling's formula, which goes, Stirling's formula states, in case you don't know, that root 2 pi n to the power n plus a half e to the minus n. So if you plug in Stirling's formula, that'll deal with this n term, and then you plug in there, you conclude that